All right. Hello and welcome, class. Today we are going to be talking about potential energy. All right, so let's jump right in. In order to calculate potential energy, we need to go back and look at those ideas of work and power again. Okay, so let's take a step back for just a second. Here we have a fantastic problem that we're going to start off with. It has to do with the pizza guy running up these stairs. Okay, so what do we know about the pizza guy? Well, we want to know how much work does it take this pizza guy to get up the stairs. Okay, and the only thing that it's giving us here is the pizza guy's mass. We know his mass is 65 kilograms. So let's write that down. So we know our mass is equal to 65 kilograms. All right, well, how are we going to figure out how much work it takes for the pizza guy to go up the stairs? Okay, well, let's think about this. We know that work equals force times distance, right? Well, if we look here, we got another clue. We got another number. We know the distance of the stairs is 1.9 meters going up. So let's stick that on our list over here. Distance is equal to 1.9 meters. Okay. Now, in order to find the work, we need the force and the distance. We got the distance, but we need the force. So the thing you have to realize here is that as you go up, the force that you're fighting against is really the force of gravity, right? That's what you're fighting as you go up. And if that's the case, well, we know that the acceleration due to gravity is 9.8 meters per second squared. Very good, okay? So in order to find this force of gravity, all we need to do is go back to our old equation, which is force equals mass times acceleration. We'll plug our numbers in. Our mass is 65 kilograms, and our acceleration is 9.8, okay? I know I got things a little jumbled up, but let's get that number. And I think I have this set up to where if I go like this, I should get a calculator. Oh, fits perfectly. All right, so we got 65 times 9.8, and that comes out to 637. Beautiful. So I'm going to erase this, and I'm going to replace this with that number that we got. So we know our force here is 637. Well, now, in order to find work, we know work equals force times distance. I know my force is equal to 637, and my distance going up is 1.9 meters. We go back over here, see if I can do it twice in a row. I'm not going to get too cocky. Oh, does it work again? Yay! And we're going to take that answer, which is, clear this, 637 times our distance up, which is 1.9. And that gives us 1,210.3 joules of work. All right? So that is how you find how much work it takes to go up a flight of stairs, right? When you're going up, you're fighting against the force of gravity. So you got to find that force of gravity, which is equal to the mass times the acceleration. Okay? We're working with small equations, but it's seeing how they play together. Now, you may be sitting here and saying, I don't understand why we're going back and talking about work. I'll show you why, okay? Think about this. Now that this pizza guy has made it to the top of the stairs, he had to use energy to get up those stairs, right? We're starting to talk about energy. So he used energy to get up the stairs. And the question here is what happened to that energy? Okay? Did it disappear? Did it go anywhere? And the answer is it did not go anywhere, and it did not disappear, because as you're going to find out in the upcoming days, you can never create or destroy energy, right? So that energy had to be converted. It had to be turned into something else. And that something else is what we call potential energy, okay? This is why you saw that piano dangling from the string in the mountains in that first picture, okay? So what you need to understand, okay, is this conservation of energy. This is probably the most important rule in all of physics, and that rule states the very basic fact that energy can never, ever, ever be created, and it can never, ever, ever be destroyed. Okay? Well, what does that mean? Where do we get energy from? We get energy from converting energy from one source to another source. Okay? So all of the energy that exists in our universe existed at the Big Bang, okay? And since the Big Bang has just been converting, okay? From friction to heat, to the energy of movement, to the energy of sound, to the energy of light, all of these different types of energies, okay? And even into what is called potential energy, okay? So this is what we're gonna start looking at now, all right? And what you have to understand is that the total amount of energy in the universe never ever changes, okay? And again, this is gonna be a concept that we come back to. If you're sitting there going, Mr. Norris, you've been talking about this, but you haven't explained what energy is. Well, I'm sure you have a lot of ideas. When you think of the word energy, you might think of like lightning bolts, or you might think of gears moving, and that's all right, like all correct, okay? All energy is the ability to do work, okay? And if you remember, work means using a force to move an object over a distance. So the energy we talk about, whatever it is able to move an object over a distance. Okay, so let's get to today's lesson, because again, we're going to keep coming back to this, okay, this idea of energy. Today we're talking specifically about gravitational potential energy, and there's a reason we're building it up, okay? Gravitational potential energy. If you've ever heard the word potential before, potential means that something has the ability to turn into something else. It is able to transform, okay? We are talking about gravitational potential energy because we're talking about what happens when something is hanging up above the ground. Whenever anything is hanging up above the ground, like this marker, it has gravitational potential energy. Well, what do you mean when it has potential? Well, if I let go of the marker, that potential energy is turned into the energy of movement. Why does it start moving? Well, because of gravity, right? So whenever we talk today about potential energy, we're talking specifically about gravitational potential energy, okay? There's other types of potential energy. You have electrical potential energy that you find in batteries, or there's other types. But today we're just talking about what happens when you dangle something above the ground. It's got the potential to drop, okay? It's the stored energy of a position, that position being above the ground. And again, like we said, potential energy has the potential to be converted into other types of energy. In this case, we're talking very simply. If you hang something above the ground and you drop it, okay, it has the potential to turn into the energy of movement. And the equation for this, okay, our equation for today is always going to be the potential energy, gravitational potential energy, equals the mass of the object times little g, which you remember, okay, little g is our acceleration due to gravity, which is always 9.8 meters per second squared, times the height it is above the ground. It's a pretty simple equation, nothing super fancy, and we always know one of these letters, right? We always know the variable, what's not a variable, we always know g, it's a constant. G is always 9.8 meters per second squared, as long as you're on Earth. Okay, so let's keep moving forward. Oh, the unit, I forgot about this. Our unit is a unit we've seen before. The unit of energy that we use is called joules, okay? You may remember that it's the same energy we saw when we studied work, and that's gonna come back in just a second. Okay, so let's make sure we're on the same page here, all right? The higher above the ground an object is, the blank, its potential energy. What do you think fills that in? If you said greater or more or bigger or some word in that, you were correct. The higher something is off the ground, the bigger its height, the more potential energy it has, okay? That's because when it falls, it's gonna keep speeding up, and when it hits the ground, it's gonna have a ton of potential energy, okay? Also, which one of these three things has the most potential energy? Well, we got a 1 kilogram bird in each instance, So which one of these has the most potential energy? Did you say A? If you did, you'd be correct. Why? Well, because C, the bird's on the ground. It's just sitting there on the ground. It's got no potential energy. You can't fall if you're on the ground. In B, the bird is sitting on a garden chair, which is only about, maybe half a meter off the ground. A, the bird is on top of a 3-meter tree. And if you don't remember meters, a meter is just a little over 3 feet. So this is like a 10-foot tree. So because it's the highest off the ground, that is when the bird has the most potential energy. Now I want to take a second to look at these two equations, because you might be thinking to yourself, you're like, wait a second. We're measuring potential energy with joules, and we're measuring work with joules. That seems like there's something related here. And there is, okay? What you're going to come to find here, let's do a little problem so you can see how these two things are related, okay? Let's say we have a forklift, and that forklift is going to pick up a 500 kilogram package, okay? It's going to lift it up to a 6-meter shelf on a warehouse, okay? So we're taking this box, and this forklift is lifting the box up off the ground. So what do we know about the package? I can put it over there. We know that the package has a mass of 500 kilograms, and we know the distance above the ground that we're lifting it is 6 meters, right? We're trying to find how much work is done on the package. Okay, so now if you remember, okay, work equals force times distance. Okay, this was our equation from last class. We know the distance we're moving it 6 meters up, so we gotta find force. Well, again, force equals mass times acceleration. Well, we know the mass of the package. Do we know the acceleration of the package? And you might be looking up here and saying, well, we don't. But in reality, we do, right? We're lifting the package up off the ground, and what force do you fight when you lift things off the ground? Well, you fight gravity. And that acceleration is 9.8 meters per second squared. So we can easily find the force. Our force is equal to our mass, which is 500, times, we can even put a little g here, okay? That's the force of gravity, times our acceleration, 9.8 meters per second squared. Let me see if I can get this calculator back on the screen without screwing up too much. Let's see if I can do this. Can I do this? Over here, okay, we can see most of it. Let me clear this. So we have 500 times 9.8. If I remember correctly, this is 4,900. Yes. Boom. Let me see that. All right. So we know now our force is equal to 4,900 newtons. Excellent. Okay, so where does this get us? Well, now that we know the force, we can find the work, okay? Work equals our force, 4,900, times our distance, which is 6 meters, okay? So notice here, go back to our calculator. Again, tricky. I'm going to clear this, and I'm going to go 4,900 times our distance, which is 6 meters, and that gives us 29,400, which means that our total work is 29,400 joules. You with me? Good. All right, so let's look at something a little different. We're going to look at the exact same thing, so I'm going to leave this here, but now I want this exact same question, same size package, same distance in the air. But now I want to know how much potential energy the package has. Okay, well, our new equation is that potential energy due to gravity equals the mass of the object times the gravity, times the acceleration due to gravity, times the height off the ground. Well, do we know these things? Do we know the mass? Yep, sure do. Do we know the acceleration due to gravity? Well, yeah, we do. It's little g, it's 9.8 meters per second squared. And do we know the height off the ground? Well, yeah, it's 6 meters. It's what we call the distance. So here, we just plug those numbers in. Potential energy due to gravity equals 500 times 9.8 times 6. Mass, little g, height. Go back to our calculator, clear all out. So we have 500. Hopefully you see where this is going. Times 9.8 times 6, and look at what number that gives us. It's exactly the same. 29,400 joules of energy. Okay? It's exactly the same. It's the same that we found with the work. Okay? Our work was 29,400 joules, and our potential energy is 29,400 joules. Why is that? Well, we have to go back here. These two equations are actually the same equation. They're saying the same thing. Well, they're saying the same thing when you're lifting something up off the ground. Why are they the same? Because when you're picking something up, the force you're working again is the force of gravity. And the force of gravity equals mass times the acceleration due to gravity. So here we have mass times the acceleration due to gravity times height. And to find the work, when you're picking something up, you got mass times the acceleration due to gravity times what we call distance, which is the same thing as its height. Isn't that cool? See how it's all related? Okay? All right. So now that we know that whenever you do work picking something up, okay, if I pick up the marker, okay, the energy that I use to pick up that marker does not disappear. Okay, the work that I do is converted into potential energy. Okay? They're equal. They're the same thing, right? Whatever work you do to pick something up is converted into potential energy. All right, so let's look at 3 examples here. Sorry, 2 more examples. Okay? So we have, I should have made this a little easier. All right, I can put it up here. A blank climbs a tree. We'll call him a boy. I'm assuming this is a boy. I'll have to fix it. Boy climbs up a 7.2 meter tall tree. That's high. If he has 3,100 joules of potential energy, how much mass does the boy have? Well, let's fill in what we know. So we know the height of this tree is 7.2 meters, and we know how much potential energy he has. So we know his potential energy is equal to 3,100 joules. How much mass does the boy have? So we want to find out how much mass the boy has. All right? Well, this is actually pretty straightforward. Okay, I want to put this down here. We know the potential energy due to gravity is equal to mass times little g times the height. We can plug our numbers in. In fact, why don't I do it up here just so I can have a little more space. Potential energy is equal to, due to gravity, is equal to mass times the acceleration due to gravity times height. So this means potential energy due to gravity here is equal to the mass, which we don't know, times little g, which is 9.8, always, times the height, which is 7.2. Now, whenever you see just basic math existing in a problem, just go ahead and do it. It's the first thing you should do. Okay? So let me move this. Let me get back to my calculator. Let me clear this, and we're going to go. So we have 9.8 times 7.2. That's our little g times our height, and that gives us 70.56. All right. So now I know that my potential energy, I'm going to bring this down here, which is, oh, I forgot to plug something in. I know the potential energy. That goes right here. That's 31,000 joules, or 3,100 joules, excuse me. Been a long day. So we have 3,100 joules is equal to 70.56 times the mass. I flip these two around. If it makes it look more normal to you, you can bring the mass down here, times 70.56. Those are the same thing. Now, again, we're trying to get the mass by itself. That's what we're looking for. What's the mass of the boy? Well, look here. This is multiplication. So we have to do the opposite of multiplying, which is dividing. And you divide by 70.56, right? That's what we want to move. Whatever you do to one side, you have to do to the other. 70.56 divided by itself is 1. And we go back to our calculator to see that. Clear. We have 3,100, or 3,100, same thing, divided by 70.56. Gives me, we'll call that 44. We'll round up. Yay! How much mass does the boy have? He has 44 kilograms of mass. All right? About 110 pounds. All right, one more problem. Let's do one more, just so you guys see how this works. Okay, so remember, it's all about writing down what you know and just manipulating the equation. So let's do one more with some bigger numbers, just to get some practice in. All right, so we have a roller coaster. Let's just write down what we know about the roller coaster. The roller coaster is 8.5 times 10 to the 5th kilograms. Already know something. Our mass is 8.5 times 10 to the 5th kilograms. It starts at the top of a larger drop. Okay, it's the largest drop. If it has 5 times 10 to the 8th joules of potential energy, so I know my potential energy due to gravity is equal to 5 times 10 to the 8th joules. We're trying to figure out how high it is. So what's my height? All right, again, write down your equation. In this case, it is potential energy due to gravity is equal to, let me put this maybe here. Potential energy due to gravity is equal to mass times little g times the height. My potential energy due to gravity is 5 times 10 to the 8th. That equals my mass, which is 8.5 times 10 to the 5th. I'm going to put parentheses around these, just so we don't get confused, times little g, which is always the same. I'll put that over here. Remember, little g is always 9.8 meters per second squared. And we're multiplying that by the height. That's what we're trying to find. How high is it? Okay, so again, whenever you have basic arithmetic to do, just do it, get it out of the way. So we're going to take 8.5 times 10 to the 5th and multiply it by 9.8. So here we go. Here. Sorry if it's in the way. Let me move it up here so you can see it a little better. So we're doing, let me do parentheses. Sorry, you can't see that. 8.5 times 10. A to the b is how you get your exponent. This is why it's good to practice using this calculator, so you can know kind of how it works. Sometimes you got to start over, and that's okay. So the 5th, we move the cursor forward to bring it down and close that parentheses, and we're going to multiply that by 9.8. So remember, whenever you have scientific notation, always put it in parentheses. And this gives us 330,000. Now, we can put this into exponents. We want to move the decimal here, so we move the decimal 1, 2, 3, 4, 5, 6 times. So what does that mean? That means that this number right here just became 8.33 times 10 to the 6. We're multiplying that by the height. Bring down the other side. 5 times 10 to the 8th. Now, here we want to get the height by itself. That's what we're looking for. This is multiplication, so we do the opposite of multiplying, which is obviously dividing, and we're going to divide by this. 8.33 times 10 to the 6. Whatever you do to this side, you have to do to this side. And now, all we got to do is just practice putting our numbers in our calculator, making sure we get everything looking good, and we're going to be good to go. So let's go back up here. All right, so let me clear this out. So again, we're going to go parentheses, and we're going to take 5 times 10 to the 8th. We're going to go forward. We're going to close those parentheses, and we're going to divide that by parentheses 8.33 times 10 a to the b to the 6th. Forward, close parentheses. I know you can't see the parentheses right there, but they're there. And here's our answer. The answer is 60 meters. That is our height right there. 60.02, which we would just round up to 60. So our height is 60 meters, which is a solid roller coaster. It's like a 200-foot roller coaster. Okay, so I know that we used some big numbers here. I know I kind of crammed it in there. I apologize for that, but go back And make sure you understand, at the heart of all of this, all we're doing is using this basic equation. Okay? Little g is always 9.8. All you got to do is know the mass, the height, and you can find the potential energy. Or if you know the potential energy and the mass, you can find the height. Or if you know the potential energy and the height, you can find the mass. We just did all three of those examples, so go back and watch them again. Put the numbers in the calculator yourself, put pencil to paper to make sure you can do it, and you're gonna do great, okay? If you got any questions, you can email me or find me for tutoring. Have a great day.